Assalamualaikum warahmatullahi wabarakatuh. Today, our group will present our power quality project. The title we choose is Analyzing Power Quality Issues and Mitigation Technique for the voltage sag, harmonic distortion, and oscillatory tension using the MATLAB simulating. So, this project focus on identify the common power quality problem and study the suitable mitigation techniques. So here is our group members. The leader is Muhammad Akid Iman bin Sharifuddin, and others are Muhammad Mustaqim, Andrea, and also me Putra Hafiz bin Azmi. So as we can see here we have the three figures about the uh, waveform. So this is about our main objective. So our main objectives in this project is to analyze three common power quality issues, which are voltage shed, harmonic distortion, and also the oscillatory tension. So for the each issue, we simulate the normal condition and the disturbance condition, and lastly the condition after the mitigation using the MATLAB simulating. So this slide show about the power quality background. So I explained about the power quality background. The power quality is referred to the ability of an electrical system to provide a stable voltage, current, and also the frequency to connect it to the load. So the poor power quality can cause equipment maybe malfunction, overheating, and reduce their efficiency, and even the system will shut down. So therefore, maintaining a good power quality is very important in the modern electrical system.
Next is the literature review. Poor quality definition is to maintain the ideal sinusoidal voltage and current waveform at the nominal frequency. It is also important to prevent the system instability and to protect the sensitive equipment from damage. So there are three highlighted disturbance in this project. The first one is the voltage sag. It is known as a brief temporary event where the electrical voltage suddenly drops below a normal level. The second disturbance is known as the harmonic distortion. It is actually a continuous distortion of the smooth ideal electrical wave. It happens when a modern nonlinear machine draws power in a choppy, irregular pulse instead of a smooth, steady stream. The third disturbance is known as the oscillatory transient. It is actually a sudden rapid change in the steady power flow that create a burst of fast, high frequency electrical ringing, which gradually fade away. So the next part is the methodology of this project. As we can see here, this is the flowchart of the methodology. The first step in our flowchart is to identify the power quality problem and continue with the literature review by collecting the data needed for our project. We also will start to develop the simulation models in the MATLAB simulating. And the next part, we will continue it by simulate a pre-disturbance condition, introduce the disturbance and apply mitigation technique. And lastly, we will analyze the result obtained. We use MATLAB Simulink for all simulation. So as we can see here, this is the simulation setup, which consists of the three-phase voltage source, a transformer, load, measurement blocks, and power glue block. Additional component were added depending on the specific power quality issue being studied. Okay, dah.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Mustaqim, DE2300098, and I'll be presenting about the voltage sag. So this slide shows the voltage set scenario used to evaluate the performance of the dynamic voltage restorer or DVR. So before the disturbance, the system operates under normal conditions with a balanced three-phase voltage of 400 volts. A double line to ground or DLG fault is then introduced, causing the voltage to drop significantly to approximately 210 volts. This represents a voltage set condition that can negatively affect the sensitive electrical equipment. To mitigate the disturbance, the DVR is activated and injects the required compensating voltage into the system, as shown in the waveform after mitigation. The voltage is restored close to its nominal value, demonstrating the effectiveness of the DVR in maintaining the power quality. And next is the voltage set test result. Under normal operating conditions, the load voltage is maintained at 230 volts RMS. When the fault occurs, the voltage decreases to approximately around 210 volt RMS, confirming the presence of a voltage set. After DVR is deployed, the voltage is successfully restored to its rated value, which indicate that DVR responds quickly to voltage disturbances and effectively compensates for the voltage drop, ensuring a stable and reliable power supply to the load during fault conditions.
Next, I will discuss the harmonic distortion power quality issue. To analyze this issue, the simulation is divided into three conditions: pre-PQ, during PQ issues, and post-PQ mitigation. For the pre-PQ condition, the system operates under normal conditions using a three-phase source, transformer, VI measurement block, and a three-phase RLC load. Since only a linear load is connected, the current remains sinusoidal and harmonic distortion is very low. Next, for the during PQ issue condition, a nonlinear load is introduced using a three-phase diode rectifier represented by the universal bridge block. The nonlinear load generates harmonic current, which distort the current waveform and significantly increase the THD level. Finally, for the post-PQ condition, a three-phase harmonic filter is installed in parallel with a nonlinear load. The purpose of the filter is to reduce the harmonic components generated by a rectifier and improve the overall power quality of the system. The impact of these three conditions can be observed from the current waveform and FFT analysis shown in the next slide. Firstly, the left side shows the normal operating condition. The three-phase current waveform is balanced and sinusoidal with a phase displacement of 120 degrees between phases. This indicates that the load behaves as a linear load and thus not introduce significant harmonics into the system. The FFT analysis confirms this condition where the THD value is only 0.31%. Since the THD is well below the IEEE standard 519 recommended limit of 5%, the system can be classified as operating under healthy power quality conditions. Next, the middle section shows the harmonic distortion condition after the nonlinear load is connected. The current waveform becomes highly distorted and exhibits a pulse-shaped characteristic instead of a smooth sinusoidal waveform. This occurs because the rectifier draws current intermittently during the AC cycle. The FFT analysis shows significant harmonic components, particularly the 5th, 7th, 11th, and 13th harmonics, which are commonly produced by 6-pulse rectifier system. As a result, the THD increased dramatically to 30.07%, indicates severe harmonic distortion. According to IEEE standard 519, this value exceeds the recommended limit and therefore the system is categorized as experiences a harmonic distortion problem. Finally, the right side shows the system after the harmonic filter is installed. Compared to the disturbance condition, the current waveform becomes smoother and more sinusoidal, indicates that part of the harmonic currents has been successfully filtered. This improvement can also be observed in the FFT analysis, where the THD is reduced from 30.07% to 21.50%. Although the THD value is still above the IEEE standard 519 recommended limit, the reduction demonstrates that the harmonic filter is effective in reducing harmonic distortion and improving the overall power quality of the system. Okay, next we move to the oscillatory transient. This case study focuses on oscillatory transient disturbance in a three-phase power system. Three operating conditions were analyzed: pre-PQ condition, PQ disturbance condition, post-mitigation condition. The oscillatory transient was created by capacitor bank switching at 0.1 second, while an RC snubber circuit was applied as a mitigation technique. We move to the first condition, pre-PQ condition, steady state. Okay, for the circuit diagram, the system initially operates under the normal steady state condition. It consists of a three-phase source, a three-phase RLC load, and a voltage current measurement block connected to the monitoring scopes. Okay, for the VABC waveform, for the voltage one, the voltage waveform shows a balanced three-phase sinusoidal pattern with a constant amplitude and a phase displacement of 120 degrees between phases. No disturbance are observed. For the IABC waveform, for the current, similarly, the current waveform remains balanced and sinusoidal throughout the simulation period. This indicates stable system operation and serves as the reference condition before any disturbance occurs. Next, we move to the during PQ issue. From the circuit diagram, to create the oscillatory transient, a capacitor bank is connected to the system through three-phase breaker. The breaker closes at 0.1 second, causing a sudden switching event. From the VABC waveform, voltage, at the switching instant, high-frequency oscillation appear in the voltage waveform. This transient disturbance causes temporary waveform distortion before gradually returning to the normal operation. From the IABC waveform current, the current waveform experiences a more noticeable oscillatory response due to the sudden capacitor energization. High-frequency oscillations with less amplitude can be observed immediately after switching. And the last part is the post-PQ condition after mitigation. From the circuit diagram, an RC snubber circuit is introduced across the switching device to suppress the transient energy generated during capacitor bank switching. From the VABC waveform, voltage, after applying the RC snubber circuit, the voltage oscillations are significantly reduced. The waveform returns to its normal sinusoidal shape more quickly compared to the disturbance condition. From the IABC waveform, the current waveform also shows a reduction in oscillation magnitude and duration. The transient energy is dissipated by the snubber circuit, resulting in faster damping and improved waveform quality.
Greeting, my name is Andrea Kolia Ananoheng. So for the next part is the conclusion. There are three PQ issues which are successfully simulated in this project, and we can see that the disturbance significantly affect the system performance, but each of the disturbance have its own solution. The first one is DVR restored the voltage during sagging, and the passive filter will help to reduce the harmonic distortion, while RC snubber reduce the oscillatory transient effect. And we can see that the lab simulating are proven to effective for PQ analysis. And that's all from us. Thank you.